The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
Okay, so we were in 4.5 still. Okay, and we had left off, we were talking about parallel and perpendicular lines. Okay, so we know with parallel lines, they have equal slopes. Or I should say parallel lines, as long as they're not vertical, have equal slopes. And all vertical lines are parallel to each other. We just know that vertical lines don't have a slope. It's just not defined. So that's why we make that distinction there. And perpendicular lines, whoops. These have slopes that are negative reciprocals to each other. So that's how we left off. So in the case of parallel lines, well, really in both these cases, if I know the slope for one of the lines, I know it for the other one. In the case of parallel lines, it's easy. They're just the same. In the case of perpendicular lines, if I know the slope for one line, I can get the slope for the other just by taking the reciprocal and the negative of it. So in both these cases, if we know the slope for one line, we can get the other. Okay. So what we'll see in some of the problems are we'll be told, here's some line, find the line that is parallel or perpendicular to it, but also passes through some other given point here. And if that's the case, then we can figure out what slope we need, and also the point that we're given is used to come up with the equation for the line. So let's see. So we've seen slope-intercept form. We have that. So sometimes we'll be given questions. So R are the lines y equals minus a half x plus 3 and x plus 2y equal to 10 parallel, perpendicular, or neither. Okay, so now we can answer questions like this. Well, that's not too difficult. What we're going to do is we just want to find the slope for each equation here. Now in this case, we can just read the slope off here, right? It's negative 1/2. Because that's our slope-intercept form. Okay, so for first line, y equals minus a half x plus 3. The slope is m equals minus a half. Now for this one here, we have to do a little bit of work. If I want the slope, I'm going to have to solve this for y, right? Because I want to put it into slope-intercept form here. So for the second line, we want to put the equation into y equals mx plus b form. To find the slope. And then we just compare. Okay, so we've got this. X plus 2y is equal to 10. So I just want to solve this for y, so I'm going to subtract x. And then I would have 2y is equal to negative x plus 10. And now we're just going to divide by 2. So what I get is y is equal to, now this first one here will be minus a half x plus, and then 10 divided by 2 is 5. Okay, and here also we see the slope is negative 1/2 here. Okay, so these lines have the same slope. So again, here we get m equals minus a half. So since these both have the same slope, we can see they have different intercepts here as well. These lines are parallel. So these are parallel lines. Okay, so not super difficult to check on that. Okay, so any questions there?
So in order to put something in slope-intercept form, you take whatever variable you're trying to find and then isolate it, and then...
Well, slope-intercept form means we solve for y, so y is the variable that you want to isolate in that case. Okay. So that's pretty much the last bit for 4.5 here. So now we want to move on into section 6. So here what we're going to do is see, given certain pieces of information, we want to come up with an equation for a line. So if we're given the slope and the y-intercept, or the slope and a point, or even if we're given two different points on the line, because we know any 2 points make a line, we should be able to come up with an equation for that line. So that's what we want to do in this section. Okay. So equation okay. So just want to remind you about some of the different forms of the equation for a line that we have so far. We have slope-intercept form. So this is a useful one where this is where the equation is solved for x, for y, excuse me, solved for y. And then the coefficient in front of the x, that is going to be the slope of the line. And then this constant over here, b, that just tells you exactly what the y-intercept is. So we have m is equal to the slope, and then the y-intercept is just the point 0b. Okay, so this b gives us this point here, and that's where the line crosses the y-axis there. So one of the easiest ways to get the equation for a line is, if we're told what the y-intercept is and the slope, you can just immediately write down this equation here for the line. So that's pretty much easiest case scenario. So if we're given the slope and the y-intercept, we can use this equation to write the line's equation. Okay, so as an example, what is an equation for the line with slope, say, negative 2/3 and y-intercept 0, 4. Okay, well, all we're going to do is plug it into this slope-intercept form here. And we're told what the slope is, and we have the intercept here. So m in this case is just the negative 2/3, and b in this case is just positive 4 in this case. So we can just immediately write the equation down. So we have m is equal to minus 2/3, and b is equal to 4. So we just get y is equal to negative 2/3 x plus 4. Okay. So that would be an equation for this line here. It's got the appropriate slope and y-intercept here. So as far as coming up with the equation for a line, again, this would probably be the easiest. So if you're just told the slope and the y-intercept, you can just immediately write this down. There's not a whole lot of work here. You're just plugging into this formula with the slope and the intercept. So just don't mix those up, and you'll be fine. So another case is, what if you're given the slope, but you're not given the y-intercept? In other words, you're just given some other line on the point there. Or, I'm sorry, some other point on the line. That's a little more work, but not too much. So for that, we have to use a different equation. So for slope-intercept form, this is great if you have the slope and the point that you're given is the y-intercept. What if it is a different line? Or I'm sorry, I keep saying that. A different point. So we want to be able to find the equation, or I should say an equation. That's fine. Find the equation of a line given the slope and a point on the line. Okay. And again, this could be any point. It doesn't have to be the y-intercept, just any point on the line. Okay, so for this, what we use what is called the point slope formula, which is this. We have y minus y1 is equal to m times x minus x1, where m is the slope and x1, y1. So these are actual numbers here, x1 and y1. That'll be the point that you are given, like 2, 3, negative 5, 10, whatever. And x1, y1 is the given point. Okay, so there's a little more work here, but not too much. So this will be a formula that you need to know for your exams, just like the slope-intercept one as well. And this one is used when, again, we have the slope, but now the point we're given could be any point on the line. It doesn't have to be the y-intercept. Okay? So you can only use the other equation when the point that you're given is the y-intercept. This would be for every other case. Now this isn't too bad, so what we would do is plug in the slope and then the point we're given, and then we just want to clean it up a little bit to put it into slope-intercept form here. Like we want to then put it into y equals mx plus b, which won't be too much work here. All we have to do is distribute the m and then add the y1 here to the other side. So we'll do an example of this. Okay, so let's go ahead and let's find an equation of the line let's say the slope is negative 1/3, and let's say that the line passes through the point. Let's see, let's do 2, 4. Okay, so we're going to use our point slope formula here, because again, obviously this is not the y-intercept, it's just the point 2, 4 in this case. So we have the slope is negative 1/3, and we have our point. This is the x1, 2. This is the y1, 4. So we're just going to plug it into here, and then clean things up a little bit to put it into a slope-intercept form. So here's x1, y1, and that is m. So we have x1, y1, and m is equal to negative 1/3. Okay, so we're just going to plug it in here. So the point slope formula gives, I would have y minus, it's y1, so y minus y1, so that's 4 in this case, y minus 4 is equal to, and then the slope m, negative 1/3, times the quantity x minus x1, where x1 is 2, so it's x minus 2. Okay, so now we've got this, and now I just want to solve it for y. So what I'm going to do over here first is distribute the negative 1/3 through here. So I would have y minus 4 is equal to negative 1/3 x. And then I'm going to have negative 1/3 times negative 2 here, so this would be positive. And it's just going to be 2/3. Because the 2 times the 1/3 just gives you 2/3 there. So we've got this. Now I just need to add 4 to both sides and then collect like terms over here. So we're just adding 4 So I'm going to have y is negative 1/3 x plus the 2/3 and the 4. So I need to add these together, so I'm not quite done yet. Let's go ahead and add those. So let's go aside. So 2/3 plus 4. So I'm going to rewrite this as 2/3 plus. So I want to rewrite 4 with a denominator of 3. So I'm going to write that as what? 12 over 3. 12/3. So now I can just add the numerators. 2 and 12 gives me 14/3. Okay, so that's going to be my constant b here. So y is negative 1/3 x plus 14/3. So that's our equation. And now this would be, so again, we have the slope, but we can also read off the y-intercept now. The y-intercept would be 0.0, and then positive 14/3 for the y-coordinate there. But we've got this now. So this equation, again, our point-slope formula, this lets us come up with the equation for the line when the point we're given is, I mean, it could be any point on the line at all. So that is going to be useful for us. So any questions here? Okay, let's try another one of these. Okay, so go ahead and find the equation for the line with slope negative 2/5 and passing through the point 10, negative 5. Okay. Why don't you go ahead and see if you can come up with that line there and put it into a slope-intercept form. So put it into y equals mx plus b for the answer there. Okay. Anybody have an answer here? Nobody has an answer? Yeah? What'd you get?
Negative 2/5 x minus 1.
Okay. Y equals negative 2/5 x minus 1. Did anybody else get that? Yeah? Okay. Should get that. So let's go ahead and run through it. So again, we have the slope, m, negative 2/5. And then this is our point 10, negative 5. That is my x1 and my y1. Okay. And then we just plug this into the point slope formula. So point slope formula is y minus y1 is equal to m times x minus x1, like that. So just plugging these in, we have, it'll be y minus negative 5 is equal to negative 2/5 times the quantity x minus 10. Okay, so we've got this. And over here, this is y plus 5. And then distributing over here, this will be negative 2/5 x. And now the negative 2/5 times negative 10, well, we have a negative times a negative, so we know it's going to be positive. But I want to do 2/5 times 10, so 2/5 times 10 over 1, we get 5's cancel. So this is going to be 4 over 1, or just 4. So there we just get plus 4. Now all I have to do is subtract 5. So we get y is negative 2/5 x, and then 4 minus 5 is minus 1. So we get that. Questions here? Okay. So this is what we do if we have the slope and then just any point on the line. So another possibility is that what if we're just given 2 points on the line? And we want to come up with the equation from that. So let's see what we do in that situation. So we want to find an equation of a line given 2 points. Okay, so what we do is pretty straightforward. So we've got 2 different formulas for coming up with the equation for the line. The slope-intercept formula, y equals mx plus b, and the point-slope formula, that y minus y1 is equal to m times the quantity x minus x1. Well, in both those equations, we need the slope, right? If we don't have the slope, I can't really use those equations. So if we're given 2 points here, we know that any 2 points will make a line. So what we're going to do is use those 2 points to compute the slope. And then once we have the slope, we can take the slope and then either one of the 2 points that we're given, and then we use the point-slope formula there. Okay? So there's just a little bit more work here. What we need to do is compute the slope first. So that's what we want to do in this case. So one, find the slope using the given points. And I'll just call them x1 and y1 and x2 and y2, so we know that m is equal to, well, it's y2 minus y1 over x2 minus x1, okay? So if we're given these 2 points, we can compute the slope. And then once we have the slope, we can then use point slope formula, or if we get lucky and one of those 2 points happens to be the y-intercept, we can then just plug directly into the point slope formula. Okay, and then we choose a given point. So just one of the 2, it doesn't matter which one. And 3, then we use the point slope formula. Y minus y1 is equal to m times x minus x1. And then 4, write the equation in slope-intercept form. So again, more work here, not too bad. Again, first step, you would just calculate the slope from the points you're given. And then you would just go on like you would if it was a problem where you got the slope and the point. The only decision you have to make here is which one of the 2 points you're going to use for this formula. And it doesn't matter which one, but if the arithmetic is easier using one point versus the other, you know, pick the easier one to calculate with. So if one of the points you're given, if one of the coordinates is a 0, I usually pick that because 0 is going to be easy to do arithmetic with in that case. And that won't always be the case, but you know, just something to make use of. So let's do an example here. Okay, so are there any questions on this? Okay. So let's go ahead and find an equation of the line passing through the points -3, -1, and 2, -2. So this is our x1, y1, and x2, y2. And we can go ahead and label those if we want. So, and it doesn't matter which one you decide is the x1, y1, and which is the x2, y2. I just like to label them to keep everything straight so I don't mix up any coordinates or anything. So first step, we want to calculate the slope of this line. Okay, so first we want the slope, which is m is y2 minus y1 over x2 minus x1. So m is y2 is -2 minus y1 is -1. Okay, so in the numerator I've got -2 minus -1, and then x2 minus x1, x2 is 2 minus x1 is -3. So we have this. And now we just want to calculate. Okay, so here we have minus minus is plus. So this is -2 plus 1, so that's -1. And down here, again, minus minus, so that'll be plus. That's plus. That's plus. So 2 and 3 is 5. So the slope is just negative 1/5 here. Okay, that's our slope. And now all we want to do is pick one of these 2 points, and then we use the point we pick along with the slope here to come up with the equation for the line. And we're just going to be using the point slope formula. So I don't think one is going to be easier to use than the other. So now we just want to pick a point. I'm just going to go with 2, -2. And again, it doesn't matter here unless one is just going to be easier to do arithmetic with than the other. And now we're going to use the point slope formula. With the slope and this point. So I would have y minus, the y coordinate here is -2, so it's y minus -2 is equal to -1/5, the slope, times the quantity. It's x minus this x coordinate, 2 in this case. So we have this. And now we just want to put this into slope-intercept form here, and then we'll be done. Okay, so here I would have y plus 2 is equal to, and then I'm distributing here, -1/5 x. Then again, the negative times the negative will be a plus, and then the 2 times 1/5 is just 2/5. Now I just need to subtract 2 from both sides. So I get y is -1/5 x plus 2/5 minus 2. So I need to take this difference here. So let me just go aside. 2/5 minus 2. So the 2 I'm going to rewrite with a denominator of 5. So I'm going to write that as 10/5. So this is 2/5 minus 10/5. So this would be -8/5. So that's what we get. So y is equal to -1/5 x minus 8/5. So this is our line here. Y equals -1/5 x minus 8/5. So that's the process we go through. If you're given 2 points, first thing, find the slope. Then just pick one of the 2 points and use the slope and the point and the point slope formula. Okay. Questions here? Okay. Let's try one more. So let's find an equation of a line passing through the points. Let's say -4, -3, and 1, -5. So this is our x1, y1, and x2, y2. So I'm just going to go ahead and label them x1, y1, x2, y2. So first we get the slope. So m, that's y2 minus y1, over x2 minus x1. So this is going to be y2 is negative 5 minus y1 is negative 3. So I have negative 5 minus negative 3 in the numerator. x2 is 1, and then minus x1 is negative 4. Now we just want to do some arithmetic here. So minus minus, that's plus. So negative 5 and 3 is negative 2. And again, minus minus, that's plus. 1 and 4 is 5. So the slope here is negative 2/5. And now we're just going to pick a point along with the slope there to plug into the equation, slope, point slope formula. So point slope, that's y minus y1 is equal to m times x minus x1. Okay. Now here the notation is x1 and y1, but really, I mean, either of those 2 points. It doesn't matter which one you use. So I'm actually going to use this one here. So I have y minus, that y coordinate is negative 5, is equal to, it'll be negative 2/5 times x minus, that x coordinate is 1. Now we have this, and we just want to put it into slope-intercept form now. So we would have y plus 5 is equal to, and then distributing here, this will be a negative 2/5 x. And then the negative 2/5 times the negative 1 here will just be positive 2/5. Now we just subtract 5 from both sides. So we would have y is equal to negative 2/5 x, and then I have plus 2/5 minus 5, so I want to subtract those. So again, just a little arithmetic over here. 2/5 minus 5, so I need to write this with a denominator of 5. So it's going to be 2/5 minus, I'm going to write it as 25 over 5. So 2 minus 25 is negative 23 over 5. So that's what we get here. So we have y is equal to negative 2/5 x minus 23 over 5. Okay, so questions there. Okay. So now that we've got this stuff, so we can come up with the equation for a line now, as long as we know, if we know the slope and a point, we can get the equation. Or if we know 2 points, because we use those points to calculate the slope, and then use one of our equations there to get the rest. So now, like I'd mentioned before, we can now use our ideas for parallel and perpendicular lines to also figure out the slope for another line if we have a point or something. So something that can come up now is come up with an equation for a line that's parallel to some given line but passes through some other point here. So if we know that lines have to be parallel, then they have the same slope. So that's the same thing as them telling you what the slope is. Or in the case of perpendicular lines, it's the same thing as well, right? Because if we know the lines are supposed to be perpendicular to each other, then we just take the negative reciprocal of the slope we are given. So either way, we can still get the slope, and then use, one of our formulas to come up with what we want. So first, we're going to go through a couple examples where we're given a line and we say, find a line that's parallel to this one but passes through some other point. And that's pretty straightforward. So we want to find an equation of a line parallel to a given line. Okay. I'm just going to write the steps down for this. So what we do is we find the slope of the given line, right? Because if the lines are parallel, if we find the slope for the given line, that's exactly the same as the slope for the line that we want to find the equation for. Okay. So basically you're just finding the slope. Okay. And then the parallel line has the same slope, or has this same slope. And then use the slope and the given point to find an equation of the line. Okay. And depending on the point you're given, if the point you're given is a y-intercept, in that case you could just plug directly into slope-intercept formula. Otherwise, you'd have to use the point-slope formula. So you'll want to see what it is you have to use there. And then write the equation in slope-intercept form. Okay, so let's do an example of this real quick. Okay, so let's go ahead and find an equation of a line parallel to y equals 3x plus 1 that passes through the point 4, 2. Okay, so first thing we need to do is find the slope. Okay. Well, we want it parallel to this line here. Okay. Now this is nice because we can just read the slope off directly, right? We can see the slope is 3. So for this example, we want a line that has a slope of 3. Okay, so slope of the given line is 3, so our line also has slope 3. Okay? And then we've got the slope. We've got some point x1 and y1. We're going to use the point-slope formula now. Okay, so now use the point slope formula. With m equals 3 and the point for 2, this is our x1 and y1. Okay, so our formula is y minus y1 is equal to m times x minus x1. So we're just plugging all this stuff in. So we have y minus y1 is 2 is equal to m, which is 3, times the quantity x minus x1 is 4. So we've got this, and we just want to put it into slope-intercept form here. So I have y minus 2 is equal to, and I just want to distribute here, so this would be 3x minus 12. And then I just need to add 2 to both sides. So we get y is equal to 3x, and negative 12 and 2 is minus 10. Okay. And now we've got these different lines here. They're clearly parallel because they have the same slope, but they do have different y-intercepts there. So that means they're definitely not the same line, but they are parallel to each other. Okay, so in that case, it's pretty straightforward. All you have to do is find the slope. Now, sometimes if it's given to you like this, you can just read off the slope automatically. If it's not, like say it's in standard form, you would need to put it into slope-intercept form to figure out the slope that you need for your equation. Okay. We can do an example like that in a minute, but right now I just want to take a short break. We'll come back and we'll do some more examples here. Particular to a given line. Okay, so again, in this case, we know that perpendicular lines, there's still a nice relationship between the slopes of those lines. We know they're negative reciprocals to each other. So if we know one, we can figure out what the other one is. So the process is going to be very similar to when we're trying to construct a parallel line. Only difference really is when we find the slope of the given line, we then take the negative reciprocal of that. But then everything else proceeds the same way. So what we do is we find the slope of the given line, and once we have that, we can find the slope for the perpendicular line. So we find the slope of the perpendicular line by taking the negative reciprocal. Okay, and then once we have that, we're just going to use the point we're given along with one of our equations for finding the equation to get that. So now we use the given point and the point slope formula. And then we write the equation in slope-intercept form. Okay, so do an example here. Let's go ahead and find an equation of a line perpendicular to the line y equals a half x minus 3 that passes through the point 6, 4. Okay, so we need to figure out our slope, and then once we have that, we just use the point and the slope to get the equation for the line. So, well, the slope here is positive 1/2. So since we want these lines to be perpendicular, our line is going to have slope what?
-2.
Negative 2 over 1/2. So we flip it and take the negative. So you flip 1/2, you get 2, and the negative of that is just negative 2 then. So m is, we take this fraction, the 1/2, and flip it, and we take the negative. So it's negative 2 over 1, or just negative 2. Okay, so this is the negative reciprocal to 1/2. Okay, so the slope we need is negative 2. So now we've got the slope and we've got this point, so we can move ahead. So this is our x1, y1, 6, 4. And then we just use the point slope formula. So it's y minus, y1 in this case is 4, is equal to negative 2 times x minus x1 is 6. So we have this, and now we just want to put it into slope-intercept form. So y minus 4 is, distributing here, that's going to be negative 2x plus 12, and then just add 4. So we have y is negative 2x plus 16. And then these would be perpendicular to each other. Okay, so any questions there? Okay, so that's for coming up with equations for lines. So we've got lots of different examples there. So now the last section in this chapter is on graphing linear inequalities. So this is section 7. Okay, so we've seen linear inequalities before, but those were just in one variable. Now we're going to be dealing with linear inequalities with two variables, so both an x and a y. So before, if we had something like this, so say like ax plus b, say, is less than c. You know, we would go to solve this and we get something like maybe x was I don't know, greater than, I don't know, some number k, let's say. And we remember the solutions would be intervals on our real number line here. So let's say this is k. So we want everything greater than that, so we would shade it. So it would be a portion of the number line here. What we're going to see now, so if we have a linear inequality in two variables, so say I have like ax plus by is, say, less than c. What we're going to see now the solution is going to look something like this. So I'll have like a line in my plane here, and then I'm either going to be shading above the line or below the line to show where the solutions to this linear inequality are. So say this part of the graph gets shaded. So basically what we'd be saying there is our solutions to one of these linear inequalities is going to be some half of our xy plane here, you know, just as an example. I mean, obviously I'm going to go into more detail here, but that's the general thing. So in this case, when we just had one variable, we'd get like one whole section of the number line. Now we're going to get basically a half of the plane. So basically we'll graph the equivalent equation here for the line, and then we just need to figure out, are we going to be like above the line or below the line when we graph this, or shade it in or whatever. So we'll see how we do all of that. But that's the basic idea that we want to see here. So first, a linear inequality in two variables is an inequality of the form, I could have ax plus by is, say, greater than c, or it could be less than c, greater than or equal, or less than or equal. So I mean, any one of these inequality signs here, I'm not going to, it's the same expression over and over again. So really, any one of these inequality signs can be here. Okay, so anything like that is a linear inequality in two variables. And what we'll see is when we graph these, you know, it'll be something like this. It'll be some part of the plane that gets shaded in that will be a solution to this thing. Okay, so what do I mean by a solution? Well, a solution would just be an ordered pair, xy, that satisfies whatever the given equality is. So if I have, say, for example, if I had, say, x plus y is greater than 1, well, if I took the point 1, 1, so x is 1 and y is 1, that would be 1 plus 1 is 2, and 2 is greater than 1. So we would say the point 1, 1 is a solution to this thing here. So basically, solutions to these things are just ordered pairs that satisfy whatever the actual given inequality is here. So we say an ordered pair xy is a solution of the inequality if the inequality is true when we substitute the values of x and y into the inequality. Okay, so for example, just what I had here. 1, 1, whoops, is a solution to x plus y is greater than 1, since 1 plus 1 is 2, which is greater than 1. Okay. 0.11 satisfies this inequality. Now we would say negative 1 is not a solution, since negative 1 plus negative 1 is equal to negative 2, and negative 2 is not larger than 1, right? So this is not greater than 1 here. Okay, so we just want to be able to determine, which x and y's are solutions and which are not. Now, obviously, we can't write all of them down. Just like in the case with these one variable linear inequalities, I can't write all these numbers down. All I can say is, we found out x was bigger than k. So all we can say is all the numbers bigger than k. Well, there's an infinite number of numbers that are bigger than k. And what we're going to see here is, well, this is a whole half of a plane basically. We can't list all these different ordered pairs in here. There's more than we can count. So we're going to come up with a graphical representation similar to what we had here. This is basically just the two-dimensional case that we're talking about now. Okay, so any questions here? Okay. So, the line with equation ax plus by is equal to c is what we call the boundary line. That separates the region where ax plus by is greater than c. And again, this greater than, it could be any inequality symbol. So we're just saying, really in general, that separates where ax plus by is greater than c from the region ax plus by is less than c. Okay, so we've got these two different regions here. And I mean, these could be swapped. It doesn't really matter. So this is the boundary line that separates this region of the plane from this region of the plane. Okay, these are going to be two separate, non-overlapping regions of the xy plane. Right. So again, something like this. This region and this region are non-overlapping here, and the line, this would be the equation ax plus by is equal to c in this example. That's the line that separates the boundaries. So this line here, that's ax plus by is equal to c. Okay. So the related equation, so we'll have some inequality and then the related equation. The related equation creates what this boundary is from the regions that satisfy the inequality compared to the regions that would not satisfy the inequality. And it's our job to figure out, okay, well, basically what we're going to do is graph the boundary and then figure out, is this region or is this region the solution that we're looking for? So that's essentially what we're going to be doing here. Okay. Now when we graph the boundary line, we're going to have two possibilities. We'll have the possibility where the boundary line itself is included as a part of the solution, and we're going to have the possibility that the boundary line is not included, it's just a boundary. So think of it as a fence you are allowed to climb on versus one you're not allowed to climb on. Similar to, in this case, remember we would use the rounded parentheses here to show k is just the boundary here, but we can't be equal to k. Versus if we had the square brackets here, then we would say k is a part of the solution and it's also the boundary here. We're going to have a similar situation when we graph these. So to do that, we're going to use two different ways to draw the line. If we draw a solid line here, that means the boundary will be included as a part of the solution. And if the line is not included as part of the solution, in other words, it's just a boundary but not a part of the solution, we'll use a dashed line to show that. So the dashed line will correspond to this case when we use the rounded parentheses here. And a solid line would correspond to the case when we would have like a square bracket here. Okay, it's the same situation. So basically, if the inequality symbol is a greater than or equal to, or a less than or equal to, as long as we have the or equal to in there, when we draw the boundary, it'll be a solid line. If it's a strict inequality, like just greater than or just less than, we'll use the dashed line when we draw the boundary in. Okay? And it's the exact same situation as here when we would use, the rounded parenthesis or the bracket to show if we're including the boundary or not including the boundary. So solid line versus dashed line. Okay, so in the solid line case, that would be when I have something like ax plus by is less than or equal to c, or ax plus by is greater than or equal to c. So we would say that the boundary line, boundary line is included in the solution. Okay, so the graph uses a solid line. For the dashed line, that would be the case where I have, say, ax plus by is strictly less than c, or ax plus by is strictly greater than c. So in this case, the boundary line is not included in the solution. So the graph uses a dashed line. Okay, so we're kind of building our way up. So what do we do to solve these? Well, when we're given an inequality, we're going to graph the boundary line. And then depending on the inequality, it'll be a solid line or a dashed line. And then once we've done that, all we have to do is figure out, well, which region is satisfying the inequality and which region is not. Then the region that does, we shade that one to say this is our solution here. Steps. Okay, so any questions here so far? Okay, so to graph a linear inequality in two variables. So we identify and graph the boundary line. Okay, and then if the inequality is greater than or equal to or less than or equal to, we use a solid line. And then if the inequality is just strictly greater than or strictly less than, we use a dashed line. Okay, and then what we're going to do, we're going to use this thing called a test point. So we pick a point anywhere in the plane as long as it is not on the boundary line. So we pick any point from either of the two regions here. So I'm going to pick a test point over here or over here. And then what we do is we just plug that test point in to see, does it satisfy the inequality or not? Okay. So say, for example, I picked a point over here. I plug it into the inequality and we find out, yes, it does satisfy the inequality. So the region that you chose the test point from, if that test point satisfies the inequality, then that's the region that you would shade as a solution. If it doesn't, then that means this is the region that's not a solution. So that means the other region would be the solution in that case. So you only need one test point. You don't have to test both regions. You just test one. If your test point gives you a true statement, then that means the region you chose the test point from is the solution region. If it gives you a false statement, that means the other region will be the solution region. Okay, so we test a point not on the boundary. So this is important. We can pick any point we want to as long as it is not on the boundary line. But otherwise, anything else is good. Okay, and then is this a solution? In other words, does that point satisfy the inequality? Yes or no, or true or false? So then what we do is we shade on one side of the boundary line. How do we determine which side? Well, if the test point is a solution, in other words, it's you get a true statement or you say, yeah, this is a solution, is a solution, we shade on the side containing the test point. And if the test point is not a solution, we shade on the side that does not contain the test point. So if the test point is not a solution, we shade on the side that does not contain the test point. So we go back and we graph the boundary line. And we may need to use a solid line or a dashed line. Then we pick a test point that's not on the boundary line, so firmly in one region or the other. Then we use that test point to see, does it satisfy the inequality? Okay? And if it does satisfy the inequality, we shade the region that does contain the test point. If that was not a solution, so if the test point did not satisfy the inequality, then we shade in the region that does not have the test point in it. You know, so basically one side versus the other. So let's do an example here. Okay, so any questions here right now? Okay. So let's go ahead and graph the linear inequality 2x minus 3y is less than 6. So we want to graph the boundary line first. So what's the boundary line going to be? The boundary line is just replace the inequality with an equals. So that means we just graph the line, 2x minus 3y is equal to 6. So that's what we want to graph. Okay. Now when we actually draw it in, are we going to use a solid line or a dashed line here? Yeah, that's a strict inequality. So when we actually graph this line, we're going to use a dashed line here. Okay, so the boundary line is 2x minus 3y is equal to 6. So to get the boundary line, all you do, you just replace the inequality symbol with an equal sign. And now we want to graph this. So we graph, we graph this line using a dashed line. Because the inequality is a strict less than. Okay, so if I want to graph this, well, this is in standard form, and the quickest way to graph a line given to us in standard form is I'm going to find the x and the y-intercepts. So I'm going to find the x and y-intercepts, plot those 2 points, and then draw the line in. So we want to graph 2x minus 3y is 6. So I'm going to find the x-intercept. And how do I find the x-intercept? What do I do?
Making y equal to 0.
Yep, we plug in y equals 0. So let y equal to 0, and then solve for x. So I would have 2x minus 3 times 0 is 6. So that's just 0. So 2x is equal to 6. Divide by 2, and we get x is equal to 3. So this gives us the point x is 3, y is 0. So the x-intercept is the point 3, 0. And then to get the y-intercept, well, that's when I just set x equal to 0. So let x equal 0, and then we solve for y. So I would have, so I have 2 times 0 minus 3y is 6. So that drops out, and we just have negative 3y is 6. Divide by negative 3, so we get y is negative 2. And then, so this is the point 0, negative 2. Okay, so now we have those 2 points. We can plot those and then draw our boundary line. So go to the next page here. Okay, so we had the points 3, 0 and 0, negative 2. So, whoops. Okay, 3, 0 is right here, and 0, negative 2 is right here. Okay, so we've got those 2 points. And now we're going to draw the boundary line. Remember, we're using a dashed line here because we have the strict inequality there. So okay, so that's our boundary line, and it's dashed. So this tells us the boundary line itself is not a solution here. It's not part of the solution, it's just the boundary. Now we need to find a test point. So let's rewrite. So the inequality was, whoops, it was 2x minus 3y is less than 6. So we need a test point not on the boundary line. And for me, as long as the boundary line does not pass through 0, 0, I just always use 0, 0 as a test point because it's really easy to do arithmetic with. Okay, so I always just use 0, 0. The only time you can't use 0, 0 is if it happens to be on the boundary line. So in that case, you have to pick something else. But otherwise, I pretty much just always go with 0, 0 here. So we're going to pick a test point. Oops. That is not on the boundary. So I'm just going to use 0, 0. So that's right here. And now we just plug this into the inequality and see, does it satisfy the inequality there? So I would have 2 times 0 minus 3 times 0 is less than 6. Well, these are both just 0, so I get 0 is less than 6. So is that true or false there? True. Okay. So this is true. In other words, 0, 0 is a solution here. So this was our test point. This is the region that contains the test point. Since we got a true statement, that means we're going to shade everything above the dashed line here. So like this. Okay, so we shade the region containing the test point. Okay. Any questions here? Okay, let's try another one. Okay, so we want to graph this inequality. Okay, so again, first thing we're going to do is we want to graph the boundary line here. Okay, so this boundary line we're going to use solid or dashed line. Solid in this case. This is an or equal to in this case. So the boundary line is going to be the equation 2x minus y is equal to 3. We're going to graph that with a solid line. So the boundary line is 2x minus y equals 3, and we use a solid line. Okay, so again, I'm just going to find the intercepts, plot those 2 points to get the line again. So the x-intercept, again, that's when we set y equal to 0. So I have 2x minus 0 is 3. So that's just 0. So we get 2x is equal to 3. So divide by 2. And we get x is equal to 3/2, or that's 1.5, so 1.5. And now we're going to do the same thing to get the y-intercept. That's when we set x equal to 0. So for the y-intercept, set x equal to 0. So it's 2 times 0 minus y is 3. So that's just 0. So we get negative y equals 3. Well, that means y is equal to negative 3. Okay. So here, up here we have 1.50 for the x-intercept, and here we have 0, negative 3 for the y-intercept. Now we're just going to plot these 2 points and draw our line. So the inequality is 2x minus y is greater than or equal to 3. The 2 points we got were 1.50 and 0, negative 3. Okay, so here's 1 and here's 2. And here's 1, 2, and 3. Okay, so the x-intercept, that's 1.5, 0. So here's 1, here's 1.5 right here. And 0, negative 3, so 0 and then down 3, 1, 2, 3. So we are right here. Okay, and now we're going to go ahead and draw this line in, and we're using a solid line because the inequality had the equal to. So this boundary is solid. So that means the boundary itself is also a part of the solution here. Okay, so we've got this. And now we just want to pick a test point. And again, since the boundary line, the origin does not fall on the boundary line here, so we may as well use that as our test point. So I'm going to go ahead and use this. So our test point is going to be 0, 0. We just plug it in here to see what we get. So it'll be 2 times 0 minus 0 is greater than or equal to 3. So over here, this is just 0. So I get 0 is greater than or equal to 3, which is, that's not true. It's false. Okay, so this is false. Now our test point was over here, so that means we're going to shade where? On that side, yeah. So this region does contain the test point, but the test point didn't work. So that means we're going to shade this region that does not have the test point in it. Okay, so this is false. So we shade the region not containing the test point. Okay, so that's everything under here, basically. Okay. So that's our solution. And in this case, the boundary itself is also a part of the solution. So the solution goes right up to and including this line here. Whereas the other example, we could get as close as we had wanted to the boundary, but without actually touching the boundary line as part of our solution. Okay, are there any questions here? Okay, so that's basically it for this section. Yeah. So what you do to graph these is graph the boundary line, which the boundary line just comes from replacing the inequality with an equal sign. And then the line will either be solid or dashed, depending on whether the inequality has an equal sign in it or not. And then you pick a test point to figure out where you need to shade. Okay, so that's all that's going on here. So no questions there, or, okay. So that is it for chapter 4. Now we want to go and move on to chapter 5. So let's take a couple minutes and we'll start on the next chapter. We are looking at systems of linear equations. Okay, so in the last chapter we had linear equations. We were just looking at one of them. Now what we're going to be doing is looking at systems of linear equations. Now for us, you can have systems of linear equations where you've got 100 variables and 100 equations. That's an example there. For us, we're just going to be doing 2 by 2. So we'll have 2 variables and 2 equations. When you go on to Math 1000, you'll also deal with 3 variables and 3 equations. But for us, we're just doing the 2 by 2 case. But that's fine. What's really nice about systems of linear equations is basically all kind of the knowledge and intuition we get for solving 2 by 2 systems, that all carries over to higher dimensional systems as well. So whether it's 2 or 3 dimensions or even dimensions you can't visualize, like something 25 by 25 or whatever. That's not something you can picture in your head. But the tools for solving these and kind of the intuition for how you would want to go about solving them, it all carries over. So that's pretty convenient as far as that goes. Okay. So ultimately what we're going to be looking for if I've got 2 linear equations, if I were to graph those, I might get something like this. Here's one equation and its line, and here's the other equation and its line. What we're going to be looking for is where these lines intersect each other. Okay, so basically we're going to be looking for this point here. Okay. And what we're going to find, there's only 3 possibilities here. either the lines are going to intersect at one point, exactly one point, right? Because these are straight lines. They're not going to like be curving back and intersecting again somewhere. So we can get a situation like this where they intersect at exactly one point. What's another possibility we could get?
Intersecting at like half a point.
You can't intersect at half a point.
Parallel.
Parallel, so, well, this would still include perpendicular in this case here, right? Okay, but parallel lines, those, do they intersect?
No.
No, so that would be a case where there's no point of intersection. So something like this. Okay, so we've got these two cases here. So this would be, we would say, there's one solution in this case, meaning there's one point that satisfies both of these equations at the same time. That's the case where they intersect at one point. In this case, well, if the lines are parallel, they don't intersect anywhere. So there's no point where they intersect. We would say there's going to be no solution when we're looking at that system of equations. And then there's one other possibility that we're going to see. And that's actually when each equation is actually just a multiple of the other. In other words, each equation represents the same line. And in that case, so if I have something like this, and then I'll just kind of dashed line on top of it to show that they're the same line. Well, this is the case where there would actually be an infinite number of points or an infinite number of solutions to that system of equations, because every point on the line, and every line has an infinite number of points in it, every point would be a solution. Okay? So if you remember back, I think it was in chapter 2 when we were solving equations with just one variable, remember the three possibilities we could get were, we could get one solution, no solution, or infinite solutions. It's the same case here as well. So these are going to be the only three possibilities we see for solving these systems of equations. So again, in your mind you want to think about what we mean when we want to solve a system of equations is we want to see or find where they intersect each other in the plane. And there's only three possibilities there. You either get one solution, no solution, or infinite solutions. So these three possibilities cover everything. It can be hard to visualize in higher dimensions, but it's the same case there. It's always going to be one, none, or infinite. That's always going to be the case. But just for linear equations, when we talk about nonlinear equations, you can get more than one solution in that case, but we'll talk a little bit more about that later. But this is the intuition here. Just think of it as where are these lines going to intersect? That's what we're trying to figure out. So that's what's going on in this chapter. So we're interested in how do we find that solution, meaning the point that the lines intersect each other. Well, what we're going to see in the first section is we can do exactly this. We can just graph the lines and then just look and see where do they intersect each other. So that's going to be the first thing that we look at. So in section 1 here, we are going to solve systems by graphing. Okay, so first, I've kind of been throwing it around. What is a system of linear equations? That's just when we have more than one linear equation. So when two or more linear equations are grouped together, they form a system. So just examples. Okay, so this is an example of a system of linear equations here. That's another example. So by system of linear equations, we mean something like this. And they use the curly braces here to mean we're looking at both of these equations at the same time here. So we're interested in, really what we're interested in is seeing, do they intersect each other at a point, and what is that point if they do. So, solutions of a system of linear equations are ordered pairs xy that satisfy both equations at the same time. So meaning if we have a system of equations and I give you an ordered pair x, y, you just plug it into both equations and see, does it satisfy both of these at the same time? If it doesn't satisfy any of them, obviously it's not a solution. But if it satisfies one but not the other, then it's not a solution and all that. It has to satisfy both at the same time to be a solution here. So we can just check an example of that. So, are the ordered pairs 2, -2, and -2, 2 solutions to the system x minus 3y is equal to -8, and -3x minus y is equal to 4. Okay. So all we do, we just check these one at a time. So first, I'll check this point. What I do is I'm going to take 2, -2, plug it into each of these equations, see if it satisfies both of them. So let's go ahead and check 2, -2 first. So for the first equation, you'll often see me label the equations as 1 and 2, just so I can more easily refer to them. So for equation 1, plugging this in, I would have 2 minus 3 times -2. And I want this to come out to be -8. So what do we have? Well, this is minus 3 times -2. That's plus 6. So 2 plus 6 is 8. Well, that's not equal to -8. So we can actually stop at this point. Okay, it didn't even satisfy the first equation. So 2 -2 is not a solution. Okay, so 2 -2 is not a solution. Okay, so now let's go ahead and check -2, 2. So the first equation would be, it would be -2 minus 3 times 2. And again, we want this to come out to be -8. So, well, this is -2 minus 6, which is -8. Okay, so it satisfies the first equation. Now we want to see if it also satisfies the second equation. So in the second equation, it's minus 3x minus y is 4. So I would have minus 3 times minus 2 minus 2. And I want this to come out to be 4. So -3 times -2 is 6. So this is 6 minus 2 is indeed 4. Okay, so -2, 2 satisfies both equations at the same time. So it's a solution to this system. So -2, 2 is a solution to this system. Okay, and we can verify that. So let's actually just graph those equations real quick. Oh, whoops. So the first equation was x minus 3y is -8. And the other equation is minus 3x minus y equals 4. And we can see they intersect at -2, 2, which is exactly what we found there. And again, these are straight lines. In this case, this is the only point where they intersect each other. So this would be the only solution to this system of equations here. Okay, so we can see that in this case. Okay, so that's how we determine if something is a solution. So this section, again, it's mainly for building up intuition. Often for solving these systems of equations. We just work through this section on graphing it to see what the solution is. We just want to build up intuition to see what's happening. But normally what we do to solve these is we're going to use some algebraic techniques, which we'll talk about in the other two sections, or the other few sections in this chapter. But first we're going to see how we get the solution by graphing. Well, you just graph the equations, and then you just see where the lines intersect each other. Okay, so that's one way to do it. So we want to solve systems by graphing. And this is pretty straightforward. So what you do is you graph the first equation. Graph the second equation. And 3, check where the lines intersect, if they intersect. And then this is the solution. Okay, so this is going to go back to the last chapter where we have to use our techniques for graphing to graph these equations here. Okay. And again, it's going to depend on how the equation is given to you. If it's given to you in standard form, we saw that probably the quickest way is going to be to find the intercepts, plot those points, and graph the line. If it's given to you in slope-intercept form, then we'll probably want to plot the y-intercept and then use the slope to kind of walk in the correct direction and graph the line that way. Okay. So often what we'll see is that these equations are going to be given to us in standard form, so we'll often use the intercept method for plotting these lines. So let's go ahead and do an example then. So let's solve So I have x minus 3y is equal to negative 3, and x plus y is equal to 5. So I'm going to call these equations 1 and 2. And both of these are in standard form, so what I'm going to do for each of these, I'm going to use the intercept method for plotting these. So that means I need to find the x and y intercepts for this equation and for this equation. I plot those points and draw the lines, and then we just see where they intersect. Now normally for this sort of thing, if you're going to rely on graphing to solve it, you want to use graph paper, like a ruler and pencil and that sort of thing, or use some piece of technology like a graphing calculator or that website I like to use there. So I'm going to be doing this freehand, so it might not come out perfect, but we'll verify it on the computer as well so we can see that, yeah, it does actually work. But I'm going to try and do the best I can, just drawing it freehand. Okay, so first, let's find intercepts. For these lines. Okay, so for the first equation, so let's go ahead and find the x-intercept. So that's when we set y equal to 0. So I would have x minus 3 times 0 is equal to negative 3. So that drops out and we just get x equals negative 3. So that gives us the point, x is negative 3, y is 0. So we have that x-intercept, and now the y-intercept, that's when we set x equal to 0, and then solve for y. So I would have 0 minus 3y is equal to minus 3. So 0 drops out. I just have negative 3y equals negative 3. So y is equal to 1. So this would be the point 0, 1. Okay, so I've got those 2 points for that equation. So I would be able to graph that. I'm going to find all the intercepts first and then graph everything. So for the first equation, we've got our 2 points. Now we want to do that for the second equation. So again, the x-intercept is when we set y equal to 0 and then solve for x. So here, y is 0, so I would have x plus 0 is 5. So that just means x is equal to 5. So this is the point 5, 0. For the y-intercept, that's when we set x equal to 0, and then solve for y. So I would have 0 plus y is equal to 5. So this tells me that y is 5. So this is the point 0, 5. Okay, so I've got the intercepts for both of these lines now. So I can plot these, graph the lines, and then hopefully we'll be able to see where they intersect each other. Okay, so my system was this. Okay, and for this first equation, we had the points -3, 0, and 0, 1. Oops. And for the second equation, we had 5, 0, and 0, 5. Okay. Okay, first equation, going to go ahead and plot that. So -3, 0. So 1, 2, 3 to the left. -3, 0 is right here. And then 0, 1 is here. So we have that. And then the other one, we have 5, 0 and 0, 5. So 5, 0, 1, 2, 3, 4, 5, 0 is here. And 0, 5, 1, 2, 3, 4, 5 is right there. Okay. And they intersect right here. 1, 2, 3, and 1, 2. Okay, so if I drew this reasonably well, 3, 2, it looks like the solution is 3, 2. Based on that. But let's be a little more precise. So let's see what we get when I plot these here. So I have x minus 3y is -3, and x plus y is 5. Nope. Oh, 3, 2. Okay. Okay. Is that what we had?
Mm-hmm.
Oh, good. Okay. So this is a technique you can use, but you do need to be precise with it. So if you're going to do it by hand, you want like graph paper and a ruler, because I mean that's just what you want. You can always verify with technology. So if you have a graphing calculator, or I mean this website is free, you just Google graphing calculator. It's the very first result that pops up. So this can help you with that as well. So this is one way of solving these systems of equations. You literally just plot the equations and see where do these lines intersect each other. Okay, so that's one thing you can do. But again, this is mainly to help us build up intuition for solving these. In other sections, we're going to see how we use algebraic techniques to solve these. Okay, so we'll do a little bit more with this next time, just to get a little more practice here. But I mean, this is what's going on in this section. We have a system of equations, graph each equation, and just see where the solution is in that case. So any questions here? Okay. If you came in late and didn't get your exam back, I have that. Otherwise, I will see you all. Wait, do we have class next week? Yes, okay. Break is the week after, so yeah. So I will see you next Friday in a week.
Good luck with today's lesson.